Hello student, good morning. I am Dr. Ajay Kumar Sinha, Professor of Chemistry. Last class I have discussed elimination reactions. Now I am going to discuss reaction with metals. In haloalkane and haloarene, I was discussing chemical properties. Under that, last class I have discussed elimination reactions. Now I am going to discuss reaction with metals. But here one thing I want to discuss before telling reaction with metals about elimination reactions. A chemical reaction is the result of competition. It is a race that is won by the fastest runner. A collection of molecules tend to do by and large what is the easiest for them. An alkyl halide with alpha hydrogen atoms, when reacted with a base or a nucleophile, has two competing routes. Substitution means SN1 and SN2, and elimination means for the reaction which reaction will take place takes place easily, that reaction will comes first, that will be the major product, because a chemical reaction is the result of competition, maybe other possibilities also. That's why major product and minor products forms. Major product means it is easy to form, it is easy to react. Then a chemical reaction is the result of competition. It is a race that is won by the fastest runner. A collection of molecules tend to do by and large what is easiest for them, that it will do. An alkyl halide with alpha hydrogen atoms, when reacted with a base or a nucleophile, has two competing routes, SN1 and SN2. Okay, means also you can tell substitution and elimination. Which route will be taken up depends upon the nature of alkyl halide, strength and size of base or nucleophile, and reaction condition. Thus, a bulkier nucleophile will prefer to act as a base and abstracts a proton rather than approach a tetravalent carbon atom due to steric region, and vice versa. Similarly, a primary alkyl halide with a primary alkyl halide prefer a SN2 reaction. A secondary halide SN2. A secondary halide, it prefers SN2 or elimination depending upon the strength of base or nucleophile. And a tertiary halide, it follows SN1 or elimination. This is an important point. Tertiary halide, it follows SN1 or elimination depending upon the stability of carbocation or the more substituted alkene. Now I am going to discuss a reaction with metals. Most organic chloride, bromide and iodides react with certain metals to give compounds containing carbon metal bonds. Such compounds are known as organometallic compounds. Again, you listen. Most organic chlorides, bromides, iodides react with certain metals to give compounds containing carbon metal bonds. Such compounds are known as organometallic compound, because here reaction is going to take place between organic compounds and metals. That's why bond will be formed between carbon and metal. And such type of compounds are known as organic metallic compounds. An important class of organometallic compounds discovered by a scientist, chemist, Victor Grignard in 1900, that is alkyl magnesium halide, popularly known as RMGX. R means alkyl, Mg magnesium, X means halide. Okay, Grignard reagent RMGX, always you remember RMGX. R means alkyl, Mg means magnesium, X means halide, and this was discovered by a scientist. Its name was Victor Grignard in 1900, and it is known as alkyl magnesium halide. Okay, then this is a class of organic metallic compounds discovered by Victor Grignard in 1900, that is alkyl magnesium halide, RMGX, referred as Grignard reagent. What is the Grignard reagent? Then always you remember RMGX. Mg is metal, you are knowing. Mg is metal. R is alkyl group. Okay. X is halide. Then always you remember RMGX means Grignard reagent in general. These reagents are obtained by the reaction of haloalkanes with magnesium metal in dry ether. How Grignard reagent is prepared? Then it is prepared by alkyl, this haloalkanes or alkyl halide, you can tell. Haloalkanes and alkyl halides both are same. Then Grignard reagent is formed with haloalkanes and magnesium metal. When both reacts in dry ether, haloalkanes with magnesium metal in dry ether, RMGX, that is the Grignard reagent is prepared. Question is asked. Okay, then this reaction is easy. Alkyl halide, that is you can consider as a ethyl bromide, CH3 CH2 Br, ethyl bromide plus Mg, ethyl bromide plus Mg. Then here Mg is metal, you remember. Then what will happen? Magnesium is a basic nature. It can give the magnesium, Mg generally magnesium, that is of basic nature. Basic nature means it has electron. It can give electron to others. Then here what will happen? Ethyl bromide, what will happen? That when it will react with magnesium, then it can give 2 electron. Magnesium can give 2 electron. And here bromide, you know, bromine, that is the electronegative element. Then now bromine is attached to ethyl bromide. But here now magnesiums are sufficient. Quickly it will give electron. Then bromide ion, which was getting through electron through ethyl group, now it will come towards magnesium. Okay, because magnesium will now give easily electron, it will give to, can give electron to bromine. Then bromine will break the bond with ethyl group. Means bond between ethyl and bromine will break. Means carbon and bromine bond will break. Then now what will happen? That bromine now it will come to magnesium, and ethyl will also come to magnesium. Both will come to magnesium. Okay. Then here magnesium will give electron to bromine. Correct? And it will make one bond, magnesium and bromine. Bromine wanted electron. Then magnesium given one electron to bromine. Then now magnesium bromine bond formed. Now another bond, now ethyl group, that also require bond electron. Then here what will happen? That will also, this magnesium and ethyl group, they will make one bond. That is the ethyl group will attach to magnesium. Magnesium will be in the middle. It will give one electron to bromine, other electron to ethyl. Then now magnesium form two bond. One bond with ethyl, other bond with bromine. Then this is actually called a Grignard reagent. This product is called Grignard reagent, and this reaction takes place in the presence of magnesium. In the Grignard reagent, the carbon-magnesium bond is a covalent. This you remember. In the Grignard reagent, the carbon-magnesium bond is a covalent bond, but highly polar. Because why it is polar? Because magnesium is electropositive. Correct? And when it is electropositive, then it will create charge. That's why carbon-magnesium bond is covalent but highly polar. And with carbon pulling electron from electropositive magnesium. Correct? Carbon wants electron, then this electron will be given by electropositive magnesium. Correct? That's why a covalent bond will be formed. The magnesium halogen bond is essentially ionic. Question is asked that this in Grignard reagent, one bond, it is making two bond. One bond with bromine, other bond with ethyl group. Then in these two bond, two types of bonding is there. One is ionic bond. With bromine it forms ionic bond, because bromine is most electronegative, and this is not most, but it is electronegative. Fluorine is the highest, that you know, but in comparison to ethyl group, bromine is more electronegative. Then this bond will be ionic. Bond between magnesium and bromine will be ionic, but other bond will be covalent. Covalent bond is between ethyl group and ethyl group, means carbon of ethyl and magnesium. That bond is covalent. Okay. You can represent magnesium, you can write in the middle, and it will have delta positive. delta. Magnesium will have delta positive because it is electropositive, and X will be delta negative. Delta negative. R will be also delta negative. Magnesium has 2 electrons. Now both electron has been given or used in bond formation. One with X. X means maybe bromide, chloride, iodide, fluoride, and other two ethyl group or alkyl group. In general, alkyl group. Then 2 bond formed. One with alkyl group, other with halide group. That's why both halide group and alkyl group is negative charge, but magnesium will be positively charged. Grignard reagents are highly reactive. Now just importance of Grignard reagent, you see, it is very useful reagent. Okay, very useful. In many product, you will this reagent to get many product. This reagent is required. Okay, you have to give more importance for Grignard reagent. Grignard reagents are highly reactive and react with any source of proton. Any source of proton to give hydrocarbon. Okay. Grignard reagents are highly reactive and react with any source of proton. Any source of proton to give hydrocarbons. Even water, alcohols, amines are sufficiently acidic to convert them to corresponding hydrocarbons. Okay. Water, alcohol, amine are sufficiently acidic. Acidic means what? It can give the hydrogen, that is called proton. Okay, hydrogen, it will release H plus, means proton. Then remaining will be negative. Correct? As for example, H2O. Then H will leave from the H2O. H will leave as H plus. Then OH minus will be formed. Then this OH minus can react with electropositive magnesium, because magnesium has capacity to give the electron, has capacity to donate the electron and can make a bond. Correct? Then alcohol also same things. Alcohol also OH is there. Then it can donate, it can give H plus, means proton. Then O will have negative charge, because whenever hydrogen will go, it will go leaving the electron. No electron will be with hydrogen, H plus. Whatever one electron this hydrogen has, that also left and went. That's why H plus, because hydrogen has only one electron in its orbit. Okay. Then this RMGX means Grignard reagent are very reactive and react with any source of proton to give, after the reaction, what it will give? It will give hydrocarbons. Then any source of a proton, there it will react and it will give hydrocarbons. Okay. Then this one, by one example you can understand. I told you any source of proton, as for example water I told you. Same way alcohol, amine also, because amine also NH3, it can ammonia gas. Okay, that also it can give one hydrogen. Correct? Then one example I am telling you, RMGX plus H2O. RMGX plus H2O. Then now see, I told you it will give hydrocarbon. Then how it will give hydrocarbon? You can understand. Now that here R and Mg bond of grignard in presence of H2O, it will break. R and Mg bond, alkyl and Mg bond. Then R will become negative. R will become negative and Mg will become positive. Okay. Then now two charges created. R is negative, Mg is positive. Now see the H2O. It will break into H plus and OH minus. H plus and OH minus. Then now both will go to oppositely charged particles. Means R is negative, then hydrogen will go there. Hydrogen is positive plus charge, H2O, H plus and OH minus. Then this H plus will go to R minus, and it will form RH. That is called alkane. And now magnesium is positive charge, Mgx is there, only one bond broken. Then Mg is positive charge. Then now it will make bond with OH. OH minus will make bond with Mg. One plus is there. Then both will come close and it will form bond. That will be MgOH. MgOH bond will be formed. And already Mgx bond is there. Already one bond is there, Mgx. Now second bond is in the place of R. Now OH came. Hence now it is called MgOHX. MgOHX. Okay. This mechanism always you remember that RMg will break. Bond will break between R and Mg, bond will break. Means carbon of ethyl group, that bond will break. Sometimes Mgx bond will also break. Generally X will be substituted with the same type of charge, substitution. If chloride is there, can come bromide, iodide, all are same, negatively charged. Then sometimes in a special condition, exchange of X can also, exchange of X is also possible. It is therefore necessary to avoid even traces of moisture from a Grignard reagent. When Grignard reaction is going on, that time no moisture should be there. That's why dry ether is used. Why question is asked, why dry ether? Generally in the Grignard reagent, with Grignard reagent, dry ether is used. Then main reason is that it is a dry, means no moisture is there. Correct? But one solvent is also required. Then dry ether is taken because in dry ether no H2O will be there. Otherwise only this reaction will take place. RMgX plus H2O. It will form RH plus MgOHX. Then to avoid this reaction, moisture should not be there. Okay. Then it is therefore necessary to avoid even traces of moisture from a Grignard reagent. On the other hand, this could be considered as one of the methods for converting halide to hydrocarbons. Or if water will be there, then you will get hydrocarbon, RH. Okay, RH. R, suppose it was C2H5, then now you will get C2H6. If R is methyl group, then you will get methane. If it is a propyl group, you will get propane. If it is a butyl group, you will get butane, means hydrocarbon. Wurtz reaction, I am telling you, Wurtz reaction, WURTZ. It is very, very important reaction, Wurtz reaction. Alkyl halide react with sodium in dry ether to give hydrocarbon containing double the number of carbon atoms present in halide. This is important. Double the carbon means it will form hydrocarbon that will have double the number of carbons atoms present in halide. If it is one, if in it alkyl group one carbon is there, methyl as for example, then it will give hydrocarbon having 2 carbon. If it is 2, it will give 4 carbon. Hydrocarbon having 4 carbon. This remember. Okay. And this reaction is known as Wurtz reaction. Already I have discussed this reaction. Means here 2RX, 2 molecules of Grignard this alkyl halide is required. 2 molecules. Only then it will come double. 2RX. 2 molecules of alkyl halide is required. With 2 sodium, 2Na. Then now what will happen? That X bond will break. Then you will get 2R, you will get R and R. And both R will be positive charge. Here you should remember, sometimes R will be positive charge, sometimes R may have negative charge also. Already I have discussed. In the case of RMGX, R is negative, means carboanion. Negative charge means carboanion. If charge is negative on carbon, it is called carboanion. And if charge is positive on carbon, then it is called carbocation. Correct? In the reaction, this generally in the form of intermediate it is formed. Then this carbon can form, means this halide can form carbocation also, anion also, depending upon from which it is reacting. This is reacting with whom? It depends upon that. If it is a Mg, then what will happen? You understood? That now this R will become negative. Okay. But now here with sodium, 2Rx plus 2Na, then now this X bond, Rx bond will break. Then it will provide 2X minus and X minus, negatively charged, and R will be positively charged. Then what will happen? Now both R will come together and it will form RR bond it will form, and 2X is there, then it will react with 2 sodium. Okay, then each sodium is 1 positive and this 2 chloride is 1 negative, hence it will form 2NaCl or 2NaX. X means halide. Then here actually this reaction when it bond will break, R and X bond will break, then R will take its electron. 1 electron will be with R. Then 2 R is there, both have 1 electron. That's why by sharing R and R, both R have 1 electron, hence they can make 1 bond between R and R. Okay, in electrolysis, generally this reaction takes place. Now, other reaction I am telling you, reaction of, now this haloalkane I have finished. Reaction, chemical properties of haloalkane I have finished. Now I am going to discuss haloarene. Haloarene related to benzene ring. Okay, in benzene ring 1 chloride will be there, 1 H will go, other in its place other halide may come. X you can tell in general, C6H5X. X may be fluoride, chloride, bromide, iodide, etc. Then that I am telling you reactions of haloarene. Okay. Then here also, just like haloalkane, reaction will repeat. Similar type of reaction will be there. Then here also nucleophilic substitution will take place. Nucleophilic substitution will take place. Then here nucleophilic substitution means always you are knowing that nucleophile will have negative charge. Then substitution means it will come in the place of other. Correct? It means if X is there, X is negative charge, you know, X is negative charge, in U is also negative. Then substitution reaction will take place. Substitution reaction will take place. In the place of X, Nu will come. That's why name has been given substitution, nucleophilic substitution. Sometimes electrophilic substitution also. There E means electrophile. Electrophile has positive charge. Then positive charge, this here that substitution will be with positive only, because E is positive, E plus, then it will take place of H plus. H plus will go and E plus may come. Charge should be same. Charge should be same. Okay, that is the substitution. And in nucleophilic substitution, process is two, that it can take place in sometimes in one step. Then one step means SN2 reaction. Sometimes in two step. Then two step means SN1. Reverse, name is SN1, but two step. And SN2, name is SN2, but the step is only one. Don't forget. Okay. Then here also in haloarenes or aryl halide, aryl, A-R-Y-L, aryl halide reaction, nucleophilic substitution also takes place. Aryl halides are extremely less reactive towards nucleophile. This is the limitation. Aryl halides are extremely less reactive towards nucleophilic substitution reaction. Why? Then this is due to resonance effect. Resonance effect. Now you take example of chlorobenzene. One Cl is attached with carbon, and carbon is this attached with one benzene, carbon of benzene. Then benzene triple bond is this the three double bond is there, alternate double and single bond is there. Now suppose where double bond is there in benzene, only at that carbon chlorine is attached. Suppose. Then now Cl, you know that 3 pair of electrons are there. 7 electrons are there, you know. All halogen have 7 electrons in the last orbit. 7 electron. Then 3 pair will be always with halogens. In any halogens, generally 3 pair will be there. Okay, lone pair of electron, 3 lone pair of electron, and 1 electron, 7th electron will generally taking part in the reaction, and 3 lone pair of electron will be available. Then now 1 pair, when it is attached with benzene ring, that time suppose that chlorine atom is attached near the carbon, which is a double bond. Then what will happen? That one pair of electron chlorine can donate 1 pair of electron, and now actually it is attached with single bond. Then now it can make double bond. Okay, means Cl and carbon, it can form double bond. Arrow sign you can write that now always arrow sign is used where it is giving to where this chlorine is giving electron, arrow sign must be given, and it will make their double bond. Then by its arrow sign it can be shown. Then 1 pair electron it will donate and it can form double bond. But now at that carbon only within the ring already double bond was there. Already double bond was there. Then now see, if it will form double bond, then now it will be carbon will have 5 bond, because the new bond it is going to be formed, that will be double, and already one double bond is there within the ring. And 4 and 5th is attached with other benzene ring carbon, nearest carbon. 6 carbons are there, you know. Then where chlorine is attached, that carbon, that is the one, suppose you are considering, then 1, 2, 3, 4, 5, 6. Then I am telling you that now this carbon 1 and 2 double bond is there, and now carbon is going to make a bond only at that carbon. Then now total bond will be 5, because including this new 2 plus 2 plus carbon 1 and carbon 6 is also making single bond. In a benzene, you know, carbon 1 and carbon 6 already bond is there. Then now it becomes 5. It will be 5. Then carbon has maximum valency of 4. Then 5 bond it can't make. 5 bonds it can't make. Then what will happen? As soon as chlorine atom will donate 2 electron and it will make a double bond, only that moment only double bond of the benzene, means that carbon double bond is there, that bond will break and will take its electron. One bond is moving, means it will take both electron. To make a single bond, 2 electron is there, is required. Then that 2 electron will be taken, that bond will break, and 2 electron will be taken by the next carbon. Next carbon means carbon number 2, and then only double bond will be formed. Now again you can see, now that 2 electron is there at the carbon number 2. Then what will happen? That now that is negative charge, because 2 electron is there. Carbon has 2 electrons, is negatively charged. Then now it has capacity to form electron. It has capacity to form one more bond, double bond with next carbon, means carbon third. Then that 2 electron, this carbon, second carbon will make double bond between carbon 2 and 3. Then already carbon number 3 and 4 bond is there, double bond. You know, in benzene ring alternate double and triple bond is there. Then now that bond will be disturbed to maintain the covalency. That bond will be disturbed. Then now that bond also will break, and then again these 2 electron will be taken by the next carbon, means carbon number 4. Carbon number 4 will take 2 electron. Then this carbon, means carbon number 2, I told you was negative. Now carbon number 4 also negative. Same way, again it can make the bond with the next carbon. Then carbon 4 and 5, when it will make the bond double, the next double bond is there, that will be disturbed. Then now this 2 electron will give, and they will make bond between 4 and 5. Then 5 and 6 electron, that bond will break, and that electron will be taken by sixth carbon. Sixth carbon have now electron, 2 electron. Then now you can see how electron dispersed, okay, delocalized, means moved from a first carbon to sixth carbon. Negative charge moved, correct. Then carbon number 2 and carbon number 4. Carbon number 2 position is with respect to this things, first carbon Cl group, with respect to Cl group, that is the first carbon. second carbon is called what? That is called first, that is the para position, you know, that is the just fourth carbon, that will be the para position, correct, para position. And now third carbon, that will be meta position, and first carbon will be ortho position. Then first next to chloride group means chloride, that carbon is a ortho position, negative charge, and after that fourth, meta is nothing, fourth is again negative, then fourth is para, and two carbons are negatively charged. Third carbon is 6, that is also negative. Then this second and sixth are equivalent, and third and fifth are equivalent, correct. And now you have seen here that carbon number 2 and 4 is negatively charged. Hence any positive group will come there and can make the bond, correct. Why some group will come to the ortho and some group will come to the meta, some group will come again to the para? Then main reason is that where electron they will get, there positively electrophile will come, electrophile positively charged group will come there, only there where that group will get electron and will make bond, okay. Then now I understood why sometimes group will come to the ortho or para, because both ortho and para is negatively charged, okay. Then now I told you how negatively charged just delocalized, moved every carbon. Then when carbon number 6 electron will reach, after that what will happen? If now negatively charged moved through our carbon, now it came to the 6th. After reaching there, what will happen? Then now this carbon again it will make a double bond. It means between first and second double bond it will make. Then that carbon which chlorine has made double bond, that bond will break. May break, only then it can make the double bond. But here you have to understand, here we wanted to show that electron is delocalized. When chlorine will give one pair of electron, will donate, then that chlorine atom will become positively charged because one pair it has donated. Hence it will be, carbon will have positive charge, remember, and it will make double bond, correct. Then like that way here in the ring how electron is moved, delocalized, I have told you. Now you can understand that why ortho and para position some groups comes at ortho and para. Now you can understand. Then now I am telling you resonance effect. Already a structure I told you, just I will explain. In haloarenes, the electron pair on halogen atoms are in conjugation with pi electrons of the ring. Conjugation means alternate double and single bond is called conjugation. Alternate double and single bond, that is called conjugation. Suppose if a straight chain is there, alternate double and single bonds are there, correct, then that is called conjugation. Conjugation with pi electrons. Pi electrons means here double bond, one is a single bond and other is pi bond. Then pi bond is bigger than single, hence pi bond breaks and 2 electron will be available, that can give to the other carbon. Then there where it was single, that will come double. Again it will disturb to all, then it will be just like a movement of electron from one carbon to last carbon, first carbon to last carbon, and current also can flow. Conducting polymer is due to this only flow of electron. Flow of electron is called current. Then in this type of conjugation, alternate double and single bond, movement of electron takes place like this way. And this is the main reason for conducting polymer. Polymers also conduct electricity by this mechanism. Then now I have told you that in haloarenes, but it is in benzene, it is limitation, only 6 carbon, that is in ring form. Then in haloarenes, the electron pair on halogen atoms are in conjugation with pi electrons of the ring, and the this 4 structure you will get already I have told. 4 structures are possible. C and Cl bond acquires a partial double bond character due to resonance. Due to resonance, I told you double bond character it is showing C and Cl bond. As a result, the bond cleavage in haloarene is difficult. Breaking cleavage means breaking. As a result, the bond cleavage in haloarene is difficult because that is the double bond. Okay, 2 double bond will be there very close. The bond cleavage in haloarenes is difficult than haloalkanes. In haloalkanes, easily bond can be broken, but here it is difficult, and therefore they are less reactive towards nucleophilic substitution reaction. Okay, their substitution reaction is not nucleophilic substitution reaction is difficult, because now Cl you can say Cl is positively charged. Cl is positively charged. Then there is no substitution. One is negative, other is positive. Okay, substitution reaction will not take place. Then this is the reason why haloarenes or aryl halides are less reactive towards nucleophile. I have nucleophilic substitution reaction. It is less, very difficult. Aryl halides are extremely less reactive towards nucleophilic substitution reaction, okay, due to the resonance effect. Now I told you about this why substitution reaction is not possible, or you can say very, very difficult. Now other reason I am telling you. First reason I told you, resonance effect. Other reason, difference in hybridization of carbon atom. Difference in hybridization of carbon atom in CX bond. In haloalkane, the carbon atom attached to halogen is sp3. In haloalkane, alkane I am talking about. In haloalkane, the carbon atom attached to halogen is sp3. This is sp3 hybridized. While in case of haloarene, the carbon atom attached to the halogen is sp2 hybridized. This is the difference. The carbon atom attached to halogen in haloarene, that is the sp2 hybridized. Okay, then this is the difference. Second reason, difference in hybridization of carbon atom in CX. Okay, the sp2 hybridized carbon with greater S character, sp2 means now one S2p is there, but in sp3 one S3p is there. Then here S character is less, but in sp2 S character is more. Remember, S character is more in sp2, but in sp3 only roughly 33%. Correct? sp3 1/3. But here you can say that sp2 has more s character, 1s 2p, but here 1s 3p. Then this is the region, the sp2 hybridized carbon with a greater s character is more electronegative because s character is more, okay, and can hold the electron pair. S character is more means it can hold the electron pair of CX bond. This is the main reason. S character, if S character is more, then they require electron. That's why if S character is more, they are more electronegative. S character is more electronegative and can hold the electron pair of CX bond more tightly than sp3 hybridized carbon in haloalkane. Okay, in comparison to haloalkane, again I am telling you, sp2 hybridized carbon with a greater s character is more electronegative and can hold the electron pair of CX bond more tightly than sp3 hybridized carbon in haloalkanes with less s character. In sp3 less s character is there. Thus CCl bond length in haloalkane is 177 pm picometer, while in haloarene it is 169 picometer. Bond length is less means a strong bond, then it will not break. And 177 is more, bond length is more means it can break easily. Okay, then it is since it is difficult to break a shorter bond, means 169 means haloarene bond is difficult to break a shorter bond than a longer bond. Therefore haloarenes are less reactive than haloalkanes towards nucleophilic substitution reaction. Two reasons I told you: bond is strong, hence it is difficult to break. Reason also I told you. Third reason I am telling you: instability of phenyl cation. In case of haloarenes, the phenyl carbon atom formed as a result of self-ionization will not be stabilized by resonance, and therefore SN1 reaction mechanism is ruled out, means it will go to SN2. Again you listen: in case of haloarenes, the phenyl cation formed as a result of self-ionization will not be stabilized by resonance, and therefore SN1 mechanism is ruled out, means reaction will take place only in one step. SN2 is somewhat possible. It is possible, not the SN1 reaction. And SN1 mechanism is ruled out. Now this fourth reason, third reason I told you: instability of phenyl cation. Their bond formation is not possible because it is very unstable. Correct? Now fourth reason I am telling you: because of the possible repulsion will be also there. Because of the possible repulsion means it is less likely for the electron-rich nucleophile to approach electron-rich arenes. Electron-rich arene, that ring will have more electron, and nucleophile will also have electron. also have electron, then there will be repulsion. Both have electron. In the same charge, repulsion takes place. Then this is the one more reason. Because of the possible repulsion, it is less likely for the electron-rich nucleophile to approach electron-rich arenes. Okay. Then I told you why nucleophilic substitution reaction is less reactive, extremely less. Aryl halides are extremely less reactive towards nucleophilic substitution reaction. I have discussed 4 reasons. Now I am telling you replacement by hydroxyl groups. Replacement by hydroxyl groups. Chlorobenzene can be converted into phenol by heating in aqueous sodium hydroxide. Chlorobenzene can be converted into phenol, means alcohol, phenol. How? By heating in aqueous sodium hydroxide NOH solution at a temperature, high temperature 623 Kelvin and a pressure of 300 atmospheres. 2 conditions are there, high temperature and high pressure. 623 Kelvin temperature and pressure 300 atmospheric pressure. And what is required here? Then sodium hydroxide, aqueous, means sodium hydroxide must be dissolved in water. Then now chlorobenzene plus NOH reaction will take place. And what will happen here? NaOH is there, NaOH. Then here what will happen? That NaOH will break into Na plus OH, OH minus Na plus, Na plus. Then Na will go to the Cl. Na will go to the near the Cl. Na has positive charge, Cl you know that it is negatively. Then now this bond will break. Chlorine will now go to the sodium and it will form NaCl. Then now Cl is going with electron. Then now that carbon will have positive charge. That carbon will have positive charge because Cl gone. Cl is electron negative element. Always it will go with electron. They want electron. Then it went just Cl minus. Na plus was there. It formed NaCl. Now that carbon is lagging electron. Now that carbon became positively charged because its electron also taken away by chlorine. Then now this carbon will, near this carbon, OH minus will come. OH minus has electron, that will come and will make a bond. OH bond will be formed. OH and carbon will make one bond. Then now benzene has one OH group. That's what is called phenol. Okay. The presence of electron, now I am telling you that what I discussed, para and ortho position, that things now we will observe. The presence of an electron withdrawing group. Electron withdrawing group means it can withdraw electron, it can take the electron, like NO2. NO2 is positively charged. NO2, N is positively charged. Because with N2 oxygen is attached, NO2, then N electron has been taken by 2 oxygen. Then N is positively charged. And now where it will go? This electron withdrawing group. All groups which have positively charged are called electron withdrawing groups. You remember, in a molecule, any atom, if have positive charge, it means it wants electron. Then that is called electron withdrawing group. Then where it will go? Now understanding, it is positively charged, then it will prefer to go that carbon which can give electron to it. Means ortho and para, ortho and para. Then now the presence of an electron withdrawing group at ortho and para position increases the reactivity of haloarenes. If NO2 is present at ortho and para. Now understanding why NO2 preferred in this para and meta you are knowing. And suppose it is already attached there, NO2 is attached either at para position, NO2 is attached, then what will happen? The presence of an electron withdrawing group at ortho and para position increases the reactivity of haloarenes. Haloarenes reactivity, it will increase because now it will begin to attract the electron towards itself. Then that chlorine which was attached with benzene may leave because it will not get the electron. Less electron it will get, or bond will be weaker. Bond will become weaker because NO2 group is attached. Okay. Then if NO2 group is attached with benzene, with chlorobenzene, suppose at para position NO2 is attached and NOH is there, then easily this reaction will take place. Cl will go and OH will attached and it will form nitrophenol. Correct? If suppose at para and ortho both position NO2 is there, then what will happen? Now very easily Cl will go, and its place OH will come. Then it will form 2,4-nitrophenol, 2,4-dinitrophenol. Correct? Then this I have told you. Third possibility is also there. Suppose second, 4 and 6 both are electron rich. Suppose 3 NO2 group is there and chlorobenzene is there. Then now just this Cl will, in presence of NOH, slightly will hit warm, then this Cl will go and OH will come there. Then it will form 2,4,6-trinitrophenol. It will form 2,4,6-trinitrophenol. The effect is pronounced when NO2 group is introduced at ortho and para position. This remember. The effect is pronounced when NO2 group is introduced at ortho and para position. However, no effect on reactivity of haloarene is observed by the presence of electron withdrawing group at meta position. Okay, if at meta position electron withdrawing group is there, then at meta position what you have seen? No negative charge was there, means electron was not there. When electron was not there, that carbon, then what electron withdrawing group will withdraw electron? Because it is at ortho and para negative charge. You have seen in meta position no electron was there, no negative charge. Hence, if suppose meta group is there, then presence of electron withdrawing group at meta position will not affect the reaction. Okay, no effect of reactivity of haloarenes observed by the presence of electron withdrawing group at meta position. Its mechanism I will discuss in the next class. Okay, because it is many reactions I have to tell. And next class, mechanism of the reaction when electron withdrawing group is attached, I will tell you. Thank you.